Hello, and welcome to Linear Algebra. This is lecture 4, and our topic is fields. So last time, we talked about the geometry of linear systems. So we talked about vector addition and scalar multiplication, and about viewing the solutions of linear equations as sets of vectors. This time, we're going to do a little bit of abstract algebra. We want to talk about systems with different coefficients. Okay, so far, we've been studying linear systems of equations over the real numbers. Right? And when we say that it's over the real numbers, we mean that the coefficients of the equations and the solutions have been real numbers. Okay, but in fact, if you look back, then you can see that actually we haven't even been using a lot of the real numbers. So actually, the examples we've been working with have not used any numbers like pi or the square root of 2, anything like that. We have been working with just integers and fractions. Okay, so because integers and fractions come up a lot, we have special symbols for them. So fancy Q, blackboard bold Q, represents fractions. So fractions are just P over Q, where P and Q are integers. And so we have blackboard bold Z for integers. The C comes from the German word for integers, which is Zahl, for number, Zahl. And of course, if you write P over Q, then Q cannot be 0. So far, the coefficients have been rational numbers, and the solutions have been rational numbers. Okay, and so the interesting thing to notice is that if the first thing is true, then the second one has to be true. Right, so this is bound to happen. Since the way we solve equations by using row operations, right? So let me quickly remind you, row operations mean that you can add a multiple of one row to another. So in terms of equations, you can add multiple of one equation to another. Or you could multiply an equation by a non-zero scalar. Or you can switch the order of equations. Right, so those are the row operations, and using those operations, we saw that you could get any matrix into reduced row echelon form, and so you can solve a system of linear equations. And the thing to notice is that these three operations don't leave let's say the realm of fractions, rational numbers. As long as the scalars we use are rational numbers. Oh, I think I didn't mention above, I said where the z comes from, but not the q. Of course, q stands for quotient. Right, so here the point is that if you have an equation and all of the coefficients are rational numbers, then when you're doing the row operations to solve the system of linear equations, you're never going to end up with a non-rational number, right? If you're adding a multiple of one equation to another one, okay, well, there's this multiple, right? But as long as the scalars you're using are rational numbers, as long as this multiple is a rational multiple of one equation that you're adding to another, then the numbers that you're writing down are going to keep being rational numbers. Same thing if you multiply by a non-zero rational number, an equation whose coefficients are all rational numbers, then you're going to still have an equation whose coefficients are all rational numbers, right? So as long as we start out with rational numbers, we're always going to have rational numbers. And then once we've gotten to reduced to echelon form and we can read off the solution, it's only going to involve rational numbers. On the other hand, it could be useful to consider equations in which the coefficients instead of being real numbers are maybe part of something larger. So are complex numbers, for example. Right, so here, as you know, the complex numbers are numbers that look like a plus ib, where a and b are real numbers, known as the real and imaginary part, and the and I, of course, is a number that squares to -1, right, which is not possible in the real numbers. Or, so we might want to consider things like equations with complex coefficients, or especially when thinking about computer science, it may be useful to consider equations in binary, right? So where what I mean by that is where the coefficients and the solutions can only be 0 or 1. Okay, so most generally, we can consider equations over a field. And when we want to talk about a general field, we'll use this symbol, a blackboard bold F. Right, so that's not to say that you can't consider equations with more general coefficients, but you would have to use slightly different methods or greatly different methods depending on how general you go. But as long as we're working over a field, the methods we use to solve the equations are going to be pretty much the same, as long as we keep track of what field we're working on. Okay, so what is a field? A field is a set with two operations. Okay. So just like we said, talked about vector spaces, and we said a vector space is a set, whose elements we call vectors, and those vectors have two operations. Well, we talked about vectors over Rn, so over R. So two operations, vector addition and scalar multiplication, multiplication by real numbers. In the same spirit, we're going to talk about a field abstractly. A field is just going to be a set with two operations, which are addition and multiplication, and two distinguished elements. Zero and one. And we want these two operations, the set of elements, including these two elements, 0 and 1, to satisfy the following properties. So we say such that, okay, so first, f is closed under addition and multiplication, right? So what we mean by that is if you give me any two elements in the field, then I can add them and I get something in the field, and I can multiply them and I get something in the field, right? So these two operations do not leave the set, right? Then we ask that these two operations are what's called associative. So this means that if you have three elements in the field, then it makes sense to add the three elements. So a plus b plus c. And when I do a plus b plus c, it doesn't matter if first I do a plus b and then I add c, or if first I do b plus c and then I add a. And similarly, a times b times c is unambiguous, meaning that it doesn't matter if first I do the multiplication of a times b and then c, or if I did b times c and multiplied that on the left by a. We also want these two operations to be commutative, right? So this means that if you have two elements, then it doesn't matter whether you do a plus b or b plus a, you get the same answer. And similarly, it doesn't matter if you do a times b or b times a, you get the same answer. Next, we ask that both of these have identities or neutral elements. Right? So maybe neutral elements conveys what we want better than identities. A neutral element means that when you act by this element, nothing happens, right? So if I give you an element of the field, then you can add 0 to it and nothing happens. Also, you could multiply by 1 and nothing happens, right? So there are two distinguished elements, 0 and 1, show up here. They are the neutral elements for the two operations. Also, we want these two operations to have inverses. So for every a, so this symbol, the upside down triangle, is used to abbreviate for all. right? So this reads for all A and F, there is an additive inverse, right, which we denote minus A, right, such that A plus minus A, which because of commutativity is the same as doing minus A plus A, gives us back 0, gets us back to the neutral element for addition. And then for every A and F that is not equal to 0, there is a multiplicative inverse. So this we denote A raised to the minus 1. It's an element of the field such that if I multiply A times A inverse on either side, because of commutativity, we get 1. We get back the neutral element. Okay, and then finally, we want addition and multiplication to interact well together. So final thing we ask is that these two operations distribute. So this says that if I give you any 3 elements of the field, then A times B plus C is equal to A times B plus A times C. Okay, so to summarize informally, a field is a bunch of things that you can add, multiply, subtract, and divide. Right? And that's what we want from the coefficients of a linear equation. They should be things that we can add, multiply, subtract, and divide. So notice that if you have a linear equation and you want to know if something is a solution, right, you want to be able to put this in instead of the variable. And so in order for that to make sense, you need to be able to multiply with the coefficient that's next to it. You need to be able to add with the other terms. And then if you want to solve an equation, you want to be able to undo what the coefficients are doing. And so you need to be able to subtract and divide. Okay, so let's see some examples. So first, of course, the complex numbers, as we already mentioned. So this would be all of the A plus IB such that A and B are both real numbers. And here the operations are just like for the real numbers, with the exception that I squared is equal to minus 1, right? So I expect you're all familiar with the complex numbers. So for example, the additive inverse of A plus IB is just the additive inverse of A plus I times the additive inverse of B. And if A plus IB is not 0, and I mean not 0 as a complex number, so I mean A is not 0 or B is not 0 or both. Then it has a multiplicative inverse, and the multiplicative inverse is A minus IB divided by A squared plus B squared. Right. So as you know, the complex conjugate of A plus IB is the complex number A minus IB. So you just change the sign in front of the imaginary part. That gives you the complex conjugate, and that shows up right here when you want to write down the multiplicative inverse, for example. Okay, another example. The rational numbers. And so again, this is just P over Q, where P and Q are integers, but Q is not 0. And again, this has with the same operations as the real numbers. So in fact, notice this is a subset of the real numbers, and the same operations that you use in the real numbers are the operations that you use to make Q a field. So when that happens, we say that something is a subfield. So here we would say the rationals are a subfield of the real numbers, and that means those two things. It's a subset, and it has its operations are the same operations as in the bigger set, just restricted to only use elements from the smaller set. Okay, great. So, and in turn, the real numbers you can identify as a subfield of the complex numbers. Just put b equal to 0. So let's do something completely different, right? So for binary, take f to be f2. F2 is the notation we use for the set with two elements, 0 and 1, but the set considered as a field. So it has two operations, addition and multiplication. So it's the field with two elements and operations. Okay, well, since we only have two elements, we can just write out all of the possible pairs that you would want to add and all of the possible pairs you would want to multiply as little tables. So you could start with 0 or 1 and end with 0 or 1. And then you'd want to do addition multiplication. So notice that a field has to have at least 0 and 1 because by definition, it's a set with two distinguished elements, 0 and 1. Right, so we have these two elements. And we know that 0 is the neutral element for addition. So when you add 0, nothing happens. So necessarily, this chart has this table has to be filled in partly like this, just from the fact that 0 doesn't do anything when you add. Same thing with 1 and you multiply, right? 1 doesn't do anything when you multiply. So that means that we can go ahead and fill in this like this. So that leaves us with just these two things to figure out. So this one in particular is easy because we know that every element has an additive inverse. We know that every element has a minus that, so that when you add them together, you get 0, right? And at the moment, we don't have anything that you can add to 1 to get 0. So since it has to have an additive inverse, that has to be a 0. And 1 is its own additive inverse. So in the field F2, minus 1 is equal to 1. Okay, what about over here? Well, it's also true in general, but it's not it's not in the definition. It follows from the definition that 0 plus 0, 0 times 0, 0 times anything is 0. And so in particular, 0 times 0 has to be 0. So that fills that in. Okay, so the definition and a little bit of work tells us that there's only one way you could possibly fill these in to get a field. And then it's still something to check, but I'll let you check, that if you fill in these tables in this way, that this set with these operations satisfies the definition of a field. Right, so let me point out every element is its own additive inverse, and also that the only non-zero element so 1 is its own multiplicative inverse. Okay, so similarly, for any prime p, there is a field Fp whose elements, which has p elements, we can represent them by the first p integers if you start counting from 0. So 0, 1 through p minus 1. So for p equal to 2, you have just 0 and 1. For p equal to 3, you'd have 0, 1, 2. 4 is not a prime. 5, you'd have 0, 1, 2, 3, 4, and so on. And I'll let you think about what are its operations. How do you fill in these tables so that you get a field, right? This is something you've probably heard about. It's known as modular arithmetic or as clock arithmetic, because to spoil the question or to give you a huge hint, the way it works is like a clock where the hours go from 1 to 12, and so if you want to add hours and you get above 12, well, you just subtract enough multiples of 12 till you get something in between 1 and 12, right? So if it's 11 and I want to know what time it is in 2 hours, I would add those, get 13. There isn't a 13th hour on a standard clock, so you would subtract 12 to get 1, and you'd say it's going to be 1 o'clock in 2 hours, right? So something similar works for multiplication. And if you start with a prime number, you end up with a field. Okay, now the reason that we can go from working with real numbers to working with a field and not have to work too much harder is that many so-called or seemingly obvious facts about arithmetic work in general fields. So for example, you should read theorem 1.5 in the book. And let me claim that the proofs are fun, right? So they're fun because you only have the definition to work from. So you're given these few tools, and then you're supposed to prove this. So it's like a little puzzle. It's like use these few properties to prove that this has to happen. So let's do an example. So for example, there is only one additive inverse. Sorry, that's true as well, but let's prove there's only one additive identity, so a neutral element. That is 0. Okay. If we had two of them, let's call them 0, 1 and 0, 2, are both additive identities, then, okay, so what do we know about additive identities? We know that if you add them to anything, nothing happens, right? So a neutral element for addition doesn't do anything when you add it. So what we could do is take these two additive identities and add them together, right? So we have 0, 1 plus 0, 2. And then we think, okay, if I add 0, 1, nothing happens. So adding 0, 1 is the same as just having 0, 2, right? But also, if I add 0, 2, nothing happens, right? So adding 0, 2, just 0, 1 just leaves me 0, 1, right? So this is because 0, 1 is a neutral element. And this one is because 0, 2 is a neutral element. But we're done because we've now have 0, 2 is equal to 0, 1. Right? So it turns out there was only 1 0 all along. Right? Let's do another one. So another example. Okay. If A times B is equal to 0 in a field F, then A is equal to 0, or B is equal to 0, or both of them. Right? Okay, great. So we want to show that if you multiply two things together and you ended up with 0, then one of them had to be 0. Right? So okay, so the way we'll show this is, let's consider the case when A is not 0, right? So A either is 0, in which case there's nothing to prove, or A is not 0, in which case what we need to show is that B has to be 0. Okay, now we're in the field, so from the definition, if I tell you that A is not 0, the only place where that shows up in the definition is when you're talking about multiplicative inverses, right? So what we know about non-zero elements is that there is a multiplicative inverse. Okay, so multiplicative inverse. So that means that I can, anytime when there's a multiplication by A, I could multiply by A inverse and get rid of it, right? So let's consider A inverse multiplying A times B. Okay, so first of all, we know that A times B is equal to 0, so we have A inverse times 0, and that's 0. Okay, I haven't shown that yet, but let's say you know that. On the other hand, A inverse times A times B is, by the associative property, A inverse times A times B. Right, but A inverse times A is 1 by definition of the multiplicative inverse, and by definition of multiplicative identity, 1 times B is equal to B. So if you put these two together, we see that B is equal to 0. Right? Thus, if A times B is equal to 0 and A is not 0, then B has to be 0. And that's what we wanted to show. And notice I used here something that I had already mentioned above, that if you multiply anything by 0, you get 0. That's another one of these things that are quick to prove with a fun proof. So I encourage you to do that one on your own. Okay, great. So once you have a field, then as we've been anticipating, you can study linear systems of equations with coefficients in that field. So let's define things. It's exactly as you would expect. A linear system over F of m equations in n variables is a set of equations of the form a11 x1 dot 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 a1 n xn equal to b1 dot 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 a m 1 x1 plus dot 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 a m n xn equal to bm. Right? So this where every coefficient aij is an element of the field, so all I comma j with I between 1 and n, and j between 1 and n. And the products and sums in this expression are using the operations in F. Okay. Now we solve this as before by forming the augmented matrix and using row operations, right? Which, as we mentioned at the beginning, makes sense in any field. To put the matrix, the augmented matrix of the system, in reduced row echelon form. Okay, so let's do an example. Let's say find the reduced row echelon form of the matrix 0, 1, 1, 1, 0, 1, 1, 1, 0 over R and over F2, right? So a matrix is just this rectangle full of numbers. So look at this matrix. It only has the numbers 0 and 1. So it might be a matrix with the real numbers, or it might be a matrix with coefficients in F2. In fact, it could be over the complex numbers or over the rational numbers. So let's just consider these two cases, the real numbers or F2, and see what the reduced row echelon form is. Okay, so over R. Right, so we talked about how to find the reduced row echelon form before. You go one row at a time, and what you want is first that the first non-zero entry in the row be equal to 1, and then you want those non-zero entries, which are called pivots, to go from left to right as you move down the matrix, and then to get it into the reduced part of the reduced row echelon form, you want the columns that have a pivot to only have the pivot and zeros. So in this case, we look at the first row, and we want the first non-zero entry to be 1. We already have that, but since we want the pivots to move from left to right as we go down, then let's start by switching the rows, right? So we'll change order. So let's put the third row first, for example. So we switch the first and third row. So wonderful. We now have the first non-zero entry to be, oh, I think I used. So now I want to clean up its rows. So I want the other entry, sorry, this column. I want the other entries in that column to be 0. So I'll do this by adding a multiple of row 1 to row 2 and row 3. Okay, so that means nothing's going to happen to the first row. The second row, I want to get rid of this 1, so I'm going to multiply the first row by -1 and then add it to the second row. So I'll end up with a 0 here, -1 here, and 1 there. And then since I already have a 0 in that entry in the third row, nothing will happen to it. Okay, so next I look at the second row. I want the first non-zero entry to be a 1. Okay, the first non-zero entry is that one, so I should multiply by -1. Multiply 2 by -1. Okay, so nothing happens to the first row. The second row becomes 0, 1, -1, and the third row becomes 0, 1, 1. Okay, perfect. So now I have the first non-zero entry is a 1. And so that's my pivot. I want to use it to clean its column. So I want to make the rest of that column minus to have be zeros. So I'm going to achieve that by adding a multiple of row 2 to row 1 and row 3. Okay, so I'm multiplying this row by -1 and adding it to the first row. I get 1, 0, 1. I multiply this row by -1 and add it to the third row. No, nothing happens to it. And this one becomes 0, 0. I multiply this by -1, I get a 1. I add it to this one, I get 2. Okay, so now I look at the third row. I want the first non-zero entry to be a 1. The first non-zero entry is this 2, so I will multiply row 3 by 1/2. Right, so nothing happens to the first row, nothing happens to the second row, and here I end up with 0, 0, 1. Okay, so now my pivot is a 1, just like I wanted, and I will use it to clean up its columns, so I want to get rid of those. And I'll do that by adding a multiple of row 3 to row 1 and row 2. So here I end up, so I'll multiply it by -1 and add it to the first row. I end up with 1, 0, 0. I multiply it by 1, so by itself, and add it to the second row. I end up with 0, 1, 0. And then I don't do anything to the last one. And now we're done. We have a matrix in reduced row echelon form, right? Right, so let me point out that the matrix we started with has only integers in it. So in particular, we could have used as our field the rational numbers, right? You can't use as your field the integers because the integers don't form a field. You're not allowed to divide and stay within the integers, right? So while 2 is an integer, it's not 0, 1/2 is not an integer. But you could work in the rational numbers, and as you can see, we stayed within the rational numbers the whole time. Okay. Now let's do the same thing, but let's use the operations in F2. Okay, so we start the same way. So it's the same strategy. We're going to go one row at a time, and what we want is for each row to start to have first non-zero entry be a 1. We want those 1s to move to the right as we go down, and we want the rest of the column of each of those 1s to be 0s. Okay, so we'll start the same way by changing the order. Okay, so we will change the first and third rows so that we have a pivot there, and we can use that pivot to clean up the operations here, the rest of the column. So we'll do that by adding a multiple of row 1 to row 2 and row 3. Okay, so what do we want to do? We want to get rid of this 1. So in the real numbers, we said take this row, multiply it by -1, and add it to this one. Right? Okay, here, the field only has 2 elements, 0 and 1. Right? So -1, right? Remember, -1 just stands for the additive inverse of 1. So in F2, -1 is the same as 1. Right? Which is to say, to get rid of this 1, we're just going to add this row to this row. And 1 plus 1 is 0. So that'll do it. Okay, so nothing happens to the first row. We're just going to add it to the second row. So we just get 0, 1, 1. And then we don't have to do anything to the third row. It already has a 0. Okay. Now we look at the second row. We want the first non-zero entry of the second row to be a 1. Well, that's already true. So here we have our pivot. It's already a 1. We want to use it to get rid of the non-zero entries in its column. So perfect. We'll do that by adding a multiple of row 2 to row 1 and row 3. Okay. So again, minus 1 is equal to 1 in the field with 2 elements. So to get rid of these 1s, we're just going to add the second row to the first row and then add the second row to the third row. When I add it to the first row, I end up with 1, 0, 1. Second row, nothing happens. And then when I add it to the third row, I end up with 0, 0, 0. Right? Okay. And well, now we're done. This is in reduced row echelon form because every row has first non-zero entry equal to 1. Right? There's nothing to check in the third row because it's just zeros. And then those pivots, the first non-zero entries, they move to the right as you go down the matrix. And every pivot has the rest of its column equal to zeros. So it is in reduced row echelon form. Okay, but notice that the reduced row echelon form is not surprisingly different when we used different operations. What does this say about systems equations? So what does this example say about systems of equations? Okay, well, the matrix, so let me write like this. The matrix that we started with, right, this 0, 1, 1, 1, 0, 1, 1, 1, 0, this is the augmented matrix of a very simple system, right? The first, if this were an augmented matrix, then we'd have 2 columns for variables, the x column, the y column, and then the third column would be the constants. So the first row says y equals 1, the second row says x equals 1, and the last row says x plus y is equal to 0. And the reduced row echelon form we ended with over the real numbers has a pivot in the last column, right? So we know that means the system is inconsistent. The system does not have solutions. So the RREF above show that this system does not have solutions when you're working over the real numbers, and does have a solution over F2, right? Because in this case, the reduced row echelon form that we ended up with has pivots in the first 2 columns, but no pivot in the third column, right? And of course, the solution here is x equals 1, y equals 1. Okay, so not surprisingly, if you change what field you're working in, whether or not you have solutions changes. Can't change. Also notice that since F2 itself is a finite field, every finite system of equations has at most a finite number of solutions. Right? So if you have 3 different variables, well, each variable can only possibly take the values 0 and 1. So that only gives you 8 possibilities for the solutions of your system. On the other hand, since R is infinite, there can be infinitely many solutions to a finite system of equations. So as we saw last time, so even a single equation, so if you have like x plus y equal to 2, right, this has infinitely many solutions in the real numbers. Right. Okay, so let me finish off this lecture with just some historical context. So I think at this point, a fun person to mention is Évariste Galois. So Galois was alive from 1811 to 1832. So when he died, he was only 20 years old. He is a classic example of a math prodigy. He was incredibly good at math. There are lots of legends that have grown up about him, so it's not clear what actually happened. But among the legends, there's talk of him like falling asleep in class, and the professor was talking about some new result that had just been published, and he had written it up on the board when he noticed that Galois was asleep, and so he said something like, we're fortunate that we have Galois here who is going to tell us how to prove this result. And somebody wakes him up and he just walks over to the blackboard, and on the way to the blackboard, he figures out how to prove it and just proves it and then goes back to sleep at his desk. You know, that sort of thing. It's a very interesting story because of how he died. He was involved with revolutionary politics. He had a hard time getting into a good university. There was some personal tragedy in his life that happened right before his entrance exam. He took the entrance exam, which certainly didn't help. Also, apparently, he was really bad at explaining his ideas, and so you read people writing about him and saying, "Well, this kid is obviously very clever, but it's not clear whether what he's saying is true or not." But in any case, he went to jail for having threatened the life of the king. This would be Louis Philippe, right, who took the throne in 1830. And the legend, so the real story is not quite as good as the legend, but the legend says that the night before he died, he wrote to his best friend a letter where he says, "Tomorrow night, I'm going to die in a duel. And I haven't been able to get my mathematical ideas published, and I don't want them to die with me. And so I'm writing them to you in this letter, and I hope that you can get them published after I'm gone." And then he stayed up all night writing this letter with all sorts of important math. And then the next day he died in a duel, possibly over a woman. Other possibilities are that it was the government setting him up because he was involved with revolutionary politics. But anyway, among the mathematical ideas that he had come up with was a study of when can you solve an equation, a polynomial equation, using what are called radicals, so like square roots or cube roots or fourth roots and things like that, right? So So a first order polynomial equation is very easy to solve. It's a linear system with a single equation and a single unknown. So that's easy. A second order equation has a solution that we all know by heart. You know, if you have ax squared plus bx plus c, then we can write down the solution using square roots. Right? Cubic equation also has a solution you can write down. It's not a simple formula, but there is one. This was discovered in Italy in the 14th century, and there's a good story there that one of the first people to figure it out was Tartaglia, which means something like the person who stutters. So this was his nickname, and he back then the way you would transmit math was that you would issue a challenge to other mathematicians. Can you solve this equation? And then the other mathematicians would try to solve it. You know. So this person kept giving challenges that came down to solving a cubic equation. Right? They didn't have modern notation, but that's what it came down to. And eventually, another mathematician, Gerolamo Cardano, went and asked him, you know, obviously you know how to solve an arbitrary cubic equation. How do you do it? And Tartaglia told him that he would explain how you do it as long as Cardano promised not to publish it. Now we know about this because Cardano published it in a book called Ars Magna, or The Great Art, where he explained how to solve the cubic equation. He says something about how it's okay that he promised not to publish it, and he's publishing it anyway because what he's publishing is his own version of it and not what Tartaglia told him. But in any case, Tartaglia was very upset that this had gotten published. In the same book, Ars Magna, Cardano publishes also how you solve the equation of order 4, right? So a polynomial equation where the variables have x squared, x cubed, and x to the 4th, which had been discovered by his student, a guy called Ludovico Ferrari. Now, I know Ferrari sounds like the car, but it's just Italian for a smith. So it's a common last name. But anyway, Ludovico Ferrari had figured out how to do the equation of order 4, and that was published by his advisor Cardano in this book. And then nothing. The equation of order 5, nobody could figure out how to write down a formula for it. Euler, who was one of the greatest mathematicians ever, tried very hard to do this, and you can see places where people jokingly say that a proof that you couldn't do it is that Euler tried and he couldn't do it. But eventually, Niels Heinrich Abel, another mathematician who died very young, died at 23, of tuberculosis in his case, figured out that you couldn't do it. The people hadn't been able to do it because it wasn't possible to do. And Galois, who I brought up, figured out exactly when you give me an equation, a polynomial equation, when can its solutions be expressed using a formula involving what are called radicals, as I said, so roots. And his solution of this ushered in abstract algebra. He didn't use fields himself. He used what are called groups. But today, when you learn what's known as Galois theory, it's expressed in terms of fields and making fields larger, what are called field extensions. So you think about having like an equation with rational coefficients, and then maybe it involves square root of 2. So then you should look at the field of square root of 2 when you've, sorry, the field of the rational numbers when you've added square root of 2, things like that. So anyway, that all comes from Galois, who tragically died at the age of 20. And he really was involved politically with Republican radicals. So much so that there was a plan to do a huge riot at his funeral. But the organizers found out that a more famous person, General Lamarck, had died in between when Galois died and his funeral. And so they decided to wait and hold the riots at Lamarck's funeral. And those riots that sparked the uprising of 1832, which is the one made famous by Les Miserables. Anyway, we'll stop there and pick it up next lecture.